Everyone, this is actually attempt 2 of this video because I pushed the record button with my pinky as I was grabbing a book. So, yeah. I'll go through it really quick. I want to make this video for my friends. It's a physics problem and it's about lenses. And the type of lens I'm going to use is convex, and it refers to a type of lens for glasses or contacts you might use. So anyway, let's get to the problem. I hope you can see this. I'll read it out. Part A says, compute the position of the image of an object in the form of an arrow 5 millimeters tall, perpendicular to the lens axis, 45 centimeters to the left of the lens. And there's a bit of information we're given. The first is the radii curvature of the lens. So I'm going to type in I'm going to write down radii curvature. And you're given 2 numbers because the lens has radii on both sides, because there's 2 sides to a lens, the front and the back. And it's measured in meters. It's a very small amount. So the first one, which would be the front side, would actually be, no, this is for probably I want to think it is for the back side, because the back side has smaller surface area or smaller length. So this is 0.12 meters, and then the back side would be R2 equals 0.28 meters. So probably the front side, although I could be wrong about that. We're also given the index of the lens, which would be like the material we're working with. So as an image goes through the lens, that refers to the refraction or the bending of the image as it makes its way through the material. So let's write down that number which we're given. Index of lens. And it's not really a length, it's more of a number or a numerical value we're given. It doesn't necessarily have like a specific what am I trying to say? Like a sign or like a length or even like a real standardized value. It's more like an appropriated number. And then we have the index for air. Again, it's more like as light moves through the air, this is the amount of bending or refraction of light, literal photons, which that's how we measure light going through air. So we're given the index of air, which is basically the value of 3. Basically the value of 1. But there is a small 3 afterwards, which we take into account. So it's not a perfect numerical value of 1. We're given the object's height. So if we're looking at an object, we take that into account too, because if you don't wear glasses or you don't wear contacts or anything, actually every image that is processed through your eyes is inverted. And our own eyeballs have to take that image that is processed and realign it from being upside down to being right side up. And a lot of people really do not actually know that in physics. So the object height is actually a factor in the process of your eyeball looking at an image and taking it through the eyeball. So that is why we use h as a numerical value in this physics problem. So anyway, the object's height that we're looking at is 5 times 10 to the negative 3 meters. I hope you can see all this. And I'm not just, And then we have S. I don't know why we use S as the value, but this is the object's distance from the lens. And we're given that value as well. This is simple. It's just 0.45 meters, just a small value. Could be any sort of thing. You'd be looking at the distance of a cardboard box off in the distance of your room. You know, that the eyeball has to process and eventually reach your brain. Because your eyeballs are the only organ in your body that bypasses the peripheral nervous system, meaning that of all the organs in your body, your eyeball links directly to your brain. It does not go through the spinal cord. Like your heart, it eventually reconnects with your peripheral nervous system from the spinal cord and directly to your brain. Meaning that if you wanted to stop your heart from beating, you'd have to attack the spinal cord. Or if you wanted to stop your urinary tract or your digestive tract, you'd have to attack the spinal cord. However, if you want to stop a person from seeing, you'd have to shoot them in the brain, or you'd have to detach the eyeball directly from your head, because that is the only organ in the human body that directly attaches to your brain, the central nervous system. Anyway, I know I went kind of off topic there, but that was one of the most commonly missed problems on a biology exam I took when I was at U of M. Interesting, right? Anyway, the first thing we need to do is write down one of the most prominent formulas that we use when we want to find something like the image of an object in the form of an arrow, which we'll be finding in this problem. And that's the lens maker's formula. And it literally will give us an idea of where this object sits, the position of the image from the lens, because that's essentially what we're looking for. And it's actually kind of a little bit of a complicated formula, but once you get down to it, the biggest thing you mess up is the signs of the problems. So like making sure that not the math, but making sure the signs of the math cancel correctly. Like, did you write down the problem fine? That's fine. But are you canceling out meters? Are you making sure that like your distances are correct? That sort of thing. That's the hardest part of it. So anyway, let's write that down. The lens maker's formula. It's actually kind of a cool formula. It's 1 over F equals, in parentheses now, N2 over N1. So, hey, I'm doing a physics 1, in parentheses, multiplied by, in brackets, 1 over R1 of the radii curvature plus 1 over R2 of the radii curvature multiplied together. So let's plug in some of these formulas. Let's see. So N2 and N1, we devote that more to the index of the material that your image is going through as it reaches the lens. So let's do that, because this is going to give us a distance. Can I help you? N2 and N1. Yeah, those are we plug in the indexes for that. And N2 would be the second index we're looking for. So yeah, it wouldn't be the proprietary of air. It would be more like the index of the lens. So let's use the lens maker's formula right now. It's just 1.60 divided by 1.0003 minus 1. And we're going to multiply all this together. Multiplied by 1 over the first curvature of the lens, although it doesn't really matter because we're adding these fractions together.
Where is it, Steve?
Okay, I'm back, and I probably have to edit that shit out. I'll edit that out too. Probably won't. I don't care. Anyway. Okay, so 1 over R2 would be... I'm losing my train of thought. That would be the second radii curvature of the lens. Okay. Plus 1 over 0.28 meters. We're adding these together, and then we're taking the inverse of the I can't even think straight. We're taking the inverse of the problem to find the power of the lens. Because what we get actually in this problem, and I've already multiplied it out, so I don't, because I didn't want to sit here plugging it into a scientific calculator the whole damn time. We get 2.854 diopters, and I'll write it down. No, it's O, sorry. Diopters, which is a measurement of power we use for lenses. It's actually a specific type of focal length. So what we're supposed to do here is actually convert it to meters. And when we do that, we get this number. 0.35028 meters. And now finally we want to find the position of our image. And for that, we need to find S theta. Because actually, now that we have the power of the lens, we actually have a length finally of where that specific lens makes, the power of that lens actually makes a distance. Because we use the lens maker's formula, which gives us the specific power of an image. But if we use the thin lens formula, that will give us the position of the image. So, and it's really easy. We call it the thin lens formula. Really, all we're doing is inverting this, which we were already going to do right here. All we have to do is this part now. Invert the image, or invert the power, and that will finally give us the position of the image in this question. So let's do it. We call it the thin lens formula. I don't know why. It's still the same sort of junk, I think. Oh well. It's just 1 over 0.35028 meters equals... Where did I write that number down? Here it is. It's just a list of the answers to the math. Which seems kind of like cheating, but nah, I knew the formulas, and beforehand, I just copied down all the math answers with the formulas, because, you know, if you're going to do one thing, you might as well just do the math ahead of time, because then you don't have to, because then I won't get them wrong, like, because everyone kind of wants to move on from everything. And you don't want to sit here and say like, oh, I missed a decimal place, because I've done it on exams before and they give me like half credit. It's like, oh, it's pretty easy to do too if you're going too fast. To like use a 3 instead of a 1, and your physics is correct, but oh, oops, you put in a 2 instead of a 1. It's happened. And they give you half credit for it. Okay. Now, this one right here, compute the size of an image. That's easy too. Because we have, what's it called? I think it's called the magnetism. There's a formula for magnetism. And all it means is, we can find the size of an image, and what we use, is the object distances. So what we found last time was the position of the image of an object. Okay, the position of the image. But we already know the object's distance. Okay, you're with me? But what we can learn is we can use the magnetism equation and pair it up with the distances to find the size of the image that you are looking at when you put your glasses on. And that is what this part of the question is asking for. So a good way to get you up to speed as someone who's watching this video is to place down everything we know. Write down everything we know right now. And then I'll do the math, and it'll look a lot easier than what I'm talking about. So first off, and this comes from the first problem, or the problem we just did. S is object distance, which we were given in the first problem. And that's just 0.45 meters. And then in the last problem, what we figured out was, where is it? I wrote too many darn numbers. Okay, we figured out S1. That was the position of the image in meters, which, wait a minute, I wrote it down. There's 1.5806 meters. Okay, which was image position. 1.5806 meters. Sound easy so far? It actually is pretty easy. Yeah. Yeah. And what we want to use now is the magnetism equation to find the size of the image we're looking at. And there's a weird relationship we can use here, which this is the equation for magnetism. It's M equals H1 over H, but magnetism actually relates to the object's distance and the imaging position of a lens. So we can write a relationship here of negative S1 over S, which will give us the magnetism actually. So if we take the negative value of the image position and divide it out by the object's position, we will get the magnetism. We will get the size of the image, which is what we're looking for. We can get it using the equation for magnetism, And we can get it using the relationship of the object's distance and the image position. And that's what we're going to do. And this all makes sense due to the physics. So let's do it. Let's plug everything in. Just using those two numbers we just found. Equals negative 1.5806 meters divided by 0.45 meters. I hope you guys can see all this, really, because it's actually a really interesting problem. And this equates to a total value of m equals negative. There's that number. Okay, yeah, I knew I did the math for this. 3.512. And actually, this doesn't have a value because, again, what we're looking at. If we go up here, these cancel. These 2 meters do. So there's no attributed value to magnetism, obviously. But if you look at this and you think really closely, we aren't finished. Because we want to find the size of the object. They didn't talk about the magnetism of the object at all. Go back up to part B. It says compute the size of the image. This is us using a I can't even say the word. A magnetized viewpoint of the image. We're supposed to be using this equation. We want to find the size of the image. Actually, h1 over h. Look at this number right here below in magnetism. That's the height of the image. We can use this magnetized number, or this number that is the relationship of magnetism, to find the real value we're looking for, the height of the image. So let's create a new relationship with this equation now that we know m. Very easy, but a common misconception when doing this problem, that this is the answer. It's not. I wrote it down wrong. And it's right there. Equals h1 over 5 times 10 to the negative 3 meters. And you're like, whoa, where did I get 5 times 10 to the negative 3 meters? And you forget for a second. Let's go back some to the first page. What did they give us on the first page? They gave us the object's height, which is 5 times 10 to the negative 3rd meters. That's why we can write this relationship to find the the size of the image. Because they already gave us the object's height at the beginning. This is simple cross mathematics. And when we write it out, this relationship, we can find the actual size of the image now. Doing simple cross multiplication. So, equals and why would I want to 0.01756 meters. And I'm going to put this relationship to something that might make a little more sense. 17.56 millimeters in length. That is our size. And don't worry about the negative number. When you're working with lenses, these negative and positive numbers, it's not really a decreased value. You're not looking at nothing. These negative and positive values in reference to lenses just mean a lateral position. Are you to the left of the lens or are you to the right of the lens? Because being to the left of the lens just means you're in either a straight image that the lens doesn't have to correct. Being to the right of the lens means that you might be an inverted image that your own eyeball has to reaffirm to switch that it's right side up. Because remember, I told you at the beginning that objects that your eyeball views are actually upside down that your own eyeball has to reprocess to make right side up. I wasn't kidding about that. Your own eyeball recorrects images. That's what we mean when we put a negative number on these values or a positive number on these values. You have to think about it in the correct mode of physics. Positive and negative has a real connotation when you're doing the math. And it doesn't mean that because you've gone to a negative value, you're looking at something that's not there. Okay. Part C. Okay, yeah, we're given a few numbers for part C. I'm looking at it. Okay, here they are. Okay, I'm gonna read it out. Part C. This is the big one. This one, we're gonna draw a picture because this one's pretty easy for me to do. This is the one I'm excited about because this is the one that really tests your knowledge. And part C says a second converging lens with the same focal length is placed 3.15 meters to the right of the first. Find the position of the final image. Okay, and we're given this value. It says the second lens is 3.15 meters to the right. Okay, I'm going to write that down again just to hammer in the point. To the right. We're also given focal length 2. Focal length number 2 is 0.3502 meters. And this is where it gets fun because you'll be adding on the physics and it will make sense eventually. And the object has now changed because you added that second lens. And you have to think of it from this point. This is probably a bifocal lens at this point because a bifocal lens is two lenses. You know, like I don't really have to explain it, but a lot of times common sense, not so common. You know what I mean? So I just want to like add in the point, you know, there are lenses that have two layers, two different lenses are now added in. Just saying. For the video. Object is now 3.6 meters from lens 2. And you know, the object position would change, at least in reference to the focal length. Because when you add an amount of power, I'm talking in what's it called? Diopters, which is how we measure the power of a lens. It would change its focal length because the image would adjust accordingly based on how much power you've got on those lenses in the amount or how far away that image needs to be processed so that your own eyeball can actually focus and reaffirm that you can actually see the object. So, what do we got? What do we got? So, this is now when we're going to do a picture and write down exactly what we know. So, we're going to start with a line. And it's just, I'm going to make it as straight as possible because I lost my ruler. The object is at the end. So, we just need to draw an arrow. Here's the object. And we were told that from the second lens of... Oh, that's different. Where did I get... Where did I get... Where's that hidden number? Oh, here it is. Oh, this is the object. What am I doing? Yes, the object is 0.45 meters. Duh. From the first lens, which we did on the last problem. So we just have to write 0.45 meters from lens 1. So let's put that right there. And that would be at the end of the convex lens. So let's do that. And I like lined paper. And then the conversion, it would look just like this. Okay, shoddy, I know, whatever. Lens 1. And then we know that the image, actually we have to make an assumption here. And it's actually given to you by the physics. The image is equilateral between lens 1 and lens 2. And you're thinking, how do we know this? We know this because the second lens is 3.15 meters to the right. Think about it. And then what we found in the first problem, the first lens, lens 1, was 1.5 meters to the right that the position of the image made. And therefore, we have to assume that the image of lens 1 is equidistant from lens 2. But we're still trying to find the position of the image between lens 2 and the image. However, we can put a base distance now because the second lens is 3.15 meters to the right. It makes sense if you think about it through the physics. So image, and I'll draw the second lens. And then we can get on with the physics problem. It's not the best, but it's an okay image. An okay picture, I mean. 1.58 meters. X is right here. And we'll draw a line of 3.415 meters between the two lenses because it's equidistant. 3.15 meters. Okay, let's go. So, if you do all of this, there should be one thing coming to your mind right now. One thing. And it's this. The image created by lens 1 acts as the object for lens 2. If you do not make that assumption, you will not be able to proceed with this problem. And right now it's just a simple, okay, we got to find X, but that's easy. We already know lens 1 to the image and lens 2 to the image is equal. So let's find the object distance. We'll call it O1. If we take 3.15 meters and subtract 1.58 meters, which would be the entire focal length subtracted by lens 1's focal length to the image, we will get 1.57 meters, which makes sense. And so it's obvious. The focal length for lens 1 is the same for lens 2. And you're probably thinking, okay, what does this mean? That means that we can create a relationship based on the object and image distances that are an inverse relationship. So let's do it. 1 over 1 plus 1 over S. Because what do we, wait, did they give me that number? You're one. One minute, I'm stuck. I got that through the power equation. Okay. Okay, I know what's going on. Okay, so that number I wrote down. We're going to make a relationship based on the focal length, and we want to find S1 plus 1 over S. To find that, what we're looking for, don't forget what we're looking for, the position of the final image, which is this number right here, and we already know this relationship, which we got in the first part. So 0.35028 meters over 1 equals 1 over S1, which is the position of the final image, plus 1 over 1.57 meters. Solving it out, S1 is 0.4508 meters. Converting that to millimeters, 45.08 centimeters. Easy. And there we have it. We found the position of the final image. And it took me a while. This was a 40-minute video. And it's very typical of a question you might see at the University of Michigan. However, you have to understand that at the University of Michigan, you would get 4 of these in an exam. And you would have about 20 to 25 minutes to do one of these. And getting one question wrong out of 4 would drop your grade 25%. Thank you for watching.